Presenter today is Dr. Tae J. Kwan of the University of Alberta. He joined the University's Department of Civil and Environmental Engineering in August 2016, shortly after earning his PhD at the University of Waterloo. His current research areas include location optimization of intelligent transport, systems facilities, winter road maintenance, spatial and temporal analyses of road traffic and safety using geostatistics, GIS systems, and remote sensing, transportation, and application of big data for estimation and forecasting of road and traffic conditions. Unfortunately, Dr. Liping Fu was unable to join us today, so Dr. Kwan will be doing the entirety of the presentation. Questions can be asked in the middle. There'll be a brief break between sections for questions, as well as questions at the end of the presentation. This is being recorded for posting on the website so that others can listen and watch it in the future. And at that, I will hand it over to Dr. Kwan.
Hello. Hi. So thanks, Vicki, for your introduction. So hello, everyone. So like Vicki already mentioned, Dr. Liping Fu from the U of Waterloo joined me today in delivering the webinar due to an emergent circumstance. But so I will try my best to cover his part on quantifying the safety impact as well. I also want to express my gratitude to Dr. Liping Fu, for his support on preparing this webinar as well too. Okay, so let's get started. So in relation to the bug sustainable winter road operations, my webinar will consist of materials presented in 2 consecutive chapters. So chapters 7 and 8, as you can see here. So 7 is pertaining to safety impact, quantifying the safety impacts of winter weather and road maintenance operations, which was co-authored by Dr. Liping Fu and Dr. Temur Osman from the University of Waterloo. And the chapter 8 entails the mobility effects of winter weather and the road maintenance operations, which for which I contributed as a co-author. Okay, so I'm gonna start with some guiding questions with the hope that I can answer some of these questions or all of these questions throughout the webinar. So first question is the needs for quantifying the safety and mobility effects on winter road maintenance and weather. So this is basically what we are gathered here together to discuss what the needs are. And then after that, I'll talk about some of the factors affecting traffic safety and mobilities. And these are the key things for us to develop a good understanding of how we can quantify such effects. And then I'll go through some of the methods and the statistical analysis that we can use to quantify such effects, and followed by some of the data needs that we have to have in order for us to conduct such analysis. Okay, let's begin with the background or introductions. So as you know, during winter month, and many regions in Canada or the U.S. or any other northerly situated countries or cities experiences a high frequency of inclement weather events, and this can have a detrimental impact on the safety and mobility of motorists. And as is supported by many existing road collisions, as supported by many existing studies, road collision rates increase dramatically during inclement weather conditions due to the degradations of visibility and also traction on the roadway. And also the cost associated with the winter weather related to accidents are estimated to be $4 billion annually in North America. So there's also extensive evidence showing that the inclement weather events can affect the traffic mobility by, for instance, a loss of roadway capacity and increase the congestions and delay, as drivers must drive it at reduced speed and increase the car following distance to minimize the risk of road accidents. So to minimize the safety and mobility impacts caused by these winter weather events, it's critical that we perform snow ice controls And then we apply this systematically by integrating various winter road maintenance operations, including snow plowing, sanding, and salting. And not only efficient and effective winter road maintenance programs can reduce the risk of vehicle collisions, but can also facilitate better traffic movements. However, transportation agencies typically spend a lot of money, like around 3.3 billion annually, for conducting various winter road maintenance operations in North America, and apply about 21 million tons of salt annually, which in return brings a detrimental effect on the existing infrastructures as well as the environment. So a lot of decisions have to be made in the winter road maintenance operation at the strategic level as well as at the operational level. And one way or another, it all has the huge financial implications. So in order to make more informed decisions on this, it's critical that we have to have a quantitative understanding, where we develop a quantitative understanding of what safety and mobility impacts are. So one part is on the safety impacts and mobility impacts. So since the focus of this webinar is on quantifying the effects of winter weather and maintenance operation have on both mobility and safety, I need to reiterate the importance of such modeling exercises in this context. So we can see this, as already mentioned, the winter road maintenance provides a significant benefit to maintaining both the mobility of the highway network as well as the safety of the traveling public. But they can be very, very costly, as already illustrated. So with the models, we are able to quantitatively assess the magnitude of such effects and how it's related to the underlying weather in the winter maintenance program. So not only that, with the models, we are able to provide more objective judgment so that we can help Regional Highway Authority on developing a sustainable winter road maintenance program that is cost effective, that entails the cost effective policies and operational decisions. So you can see that, as the cost increases, maintenance cost increases, obviously the accidents and traffic delay decreases, but we can't afford to have this very high amount of high cost associated with the maintenance operation. So with the models, we can actually develop this kind of curve and determine where our optimality stands and decide accordingly, and then make more strategic operation-related decisions. Okay, first I will talk about how we can establish a mathematical relationship between the winter weather and the maintenance operations and road safety, which is first part. And later on, I'll talk about the modeling winter road mobility as well too. So by the way, feel free to ask any questions. Feel free to stop anything, stop in the middle so that I can answer any questions to the best of my knowledge. Okay. Anyway, so in order to model the winter road safety or estimate its impacts, we need to understand the factors that influence the winter road safety. So these are the factors affecting winter road safety. And as you know, all transportation engineering textbook would tell us that the accident results from the interaction of drivers, road and vehicles, which are basically the contributing factors. But if you think about it, we have a very little control over human factors, as well as the vehicles. So the best thing we could do is to consider them in the modeling process to capture their underlying driving behavior, as well as the vehicle performance or characteristic, as you can see here. On the other hand, what we can control can be road conditions, which are affected by weather and traffic and winter maintenance. And what is more intriguing is both the weather and the road condition have an effect on driving behavior. So it's important that we establish a clear link between accidents and how much winter maintenance operation can improve the road surface conditions. So in here. So there are many research conducted in the past which dedicated to establishing these factors, and then these factors to road accidents. But I'll focus on the ones that have been well received and then well included in our chapters. Although we are mostly interested in the link between accidents and winter road maintenance, we also must consider other factors such as severity of weather, level of service standards, etc., in order to obtain faithful results. So these are the factors. And in order for us to quantify the empirical relationship, so the goal here is to develop empirical models from which we can assess the quantitatively assess the impact of winter weather, and then a winter road maintenance operation on safety and mobility, we have to have the evidence, which can be represented by the data. So what evidence do we need? We need data, or we need data. We need, basically, we need three different types of data sets. And one is a road weather and condition data, and second is maintenance operation data, and third is the traffic collision or payment data. So this applies not only to safety modeling, but also the mobility effect modeling as well. So I'm not going to go too detailed on explaining this data, because I think Tina from Iowa, and then Chris from previous presenter, I think have already covered these data sources. So I'm just going to briefly touch on what they consist of and how they are used in the modeling process. So first one is the road weather condition data. It is one of the most important sources of road weather and surface condition data can be road weather information system. So for those who don't know what the RWIS is, it's basically a system that consists of many environmental weather sensors located along the side of the road and collect the various road weather data to increase the winter maintenance efficiency, and as well as to enhance the safety of the motorist. So acknowledging the tremendous amount of information it can provide to benefit the road winter related to applications, it has been implemented in many different fields, such as emergency or traffic or maintenance or changeable message signs, dynamic message signs, to help drivers make more informed decisions, while also giving timely information for the maintenance operation to decide their application type, for instance, or application rates. So in the context of winter maintenance operation, it has been considered to be one of the most effective decision support tools, specifically for anti-icing or de-icing operations. So some of the measurements that it collects include the atmospheric measurements, air temperature, dew point temperature, humidity. It also has the capability of detecting surface state or measuring the surface temperature, which is critical for any icing operations. However, we have to be careful when using this data set because since it's located along the side of the road, its measurements are static in nature, meaning that the observation collected by the system can have a limited spatial representativeness. So as you can see, the weather can have weather can vary from one location to another. Since the stationary RWIS, the RWIS that we talked about so far, is apart from other ones, anywhere between 30 to 50 kilometers, and only provides spot reading, the road condition that we analyze from the collected data may not necessarily be the same. As you can see, this is actual data set that we collected during the data collections back in 2013. And you can see that from one single location to another, you can see it undergoes severe, very different road surface conditions. And having the stationary RWIS is not able to cover this sufficiently. And to compensate that, to realizing the shortcoming of this stationary RWIS, we also used mobile RWIS that collects road weather data as it travels along the road. However, considering its data collection mechanism, it may be able to obtain the spatially representative data. But considering that the weather conditions also vary a lot over time, this may not be able to cover the temporal. It has the limited temporal representativeness. And because of this reason, the data maybe have a limited temporal coverage. Therefore, the best practice would be to combine these technology, which is worthy of another webinar. So another data set, next data set we should consider in the modeling process is the maintenance or the end operations data. And this provides a critical piece of information, as our goal is to evaluate different winter maintenance strategy related with road safety. Traditionally, many winter road maintenance agencies use the maintenance reports or logs that road patroller complete manually about the general surface conditions and what needs to be done. However, this entails manual process, which can be very time-consuming and labor-intensive. So to overcome such a limitation, many Department of Transportations have started using AVL technology. So AVL represents the automatic vehicle locations. This provides a means of automatically determining the location of vehicles. So not only collects the location information, but it also collects the distance traveled, whether spreader is on and off, an amount of material applied, and application rates. And because of all these collected information are GPS tagged, it's less prone to error and can be managed better. And most importantly, we know exactly where and how much materials were put down for how long. So this provides the critical information, especially when we want to relate this to how much it will affect the road safety as well as the road mobility. The next data set we have to have, another important source of information is the traffic data, obviously. And they're collected typically from single or dual loop detectors. And there are other technology, ITS technology, available to collect this data set. But in our case, we use the dual loop detectors that are installed on the pavement surface. And this map shows the vehicle detection stations in one of the major highways in Toronto. So we have used all this detectors to gather the traffic data. Another process data can give travel speed, traffic volume, and capacity, which are also related with the level of service. And all of these are good performance indicator or a performance measure for observing traffic flow and mobility, and also can improve the quality of safety model, as they generally have a high correlation with the collision frequency severity. So higher the traffic speed, higher the severity, higher the traffic volume, higher the collision frequency. So it's pretty much a known correlation that has been established by many researchers. Okay, last piece of information that we need would obviously be collision data. We are modeling collision, but we need to have a collision data so that we can model how the collision number changes with respect to winter weather and different maintenance strategies. So this bar chart shows the summary of total, sorry, where's my mouse go? Okay, here. So this total of collision occurred in a single segment of patrol routes in Ontario, Canada, from 2000 to 2006. And you can see, take a look at the 2001 or 2, we have about 420 collision occurred, whereas in 2002 and 3, the next year, the number of accidents were doubled during storm events. Although the severity of weather can be a driving force to have the increase in the number of collisions and should therefore be taken into considerations, it can definitely be utilized towards the performance measure and see if the maintenance standards have been satisfactorily met. So these are the data set that we could use in developing and then use this as our dependent variable Y, and use other the factors, which I already described, as our set of independent variable to explain the variation in to generate expected number of accidents. Okay, using the weather data, maintenance data, and traffic collision data, we can build models to quantitatively assess how each influencing factor would contribute to changing the collision frequency, and also quantify the magnitude of their benefits. So in short, there are two different modeling approaches that exist in the literature that differ in aggregation level and data requirements. So the first type of collision frequency model can be season-based, or also we can call this as an aggregate approach, is the data that goes into the modeling process aggregated over space or time. The model developed by Ye's group, for instance, this is the one type of work that has been well received, and they use this many maintenance routes, this many highways over 5 winter seasons. They have calibrated this equations that represents the mean collision frequency is expressed as a function of route length. The higher the route length, obviously, the higher the collision frequency, and the higher the ADT, which represents the average daily traffic or exposures. Higher it is, the higher the mean collision frequency, and then as a function of exponential function of material cost of route. So this represents the winter maintenance operation part. So higher the cost of maintenance routes, and then it has a negative correlation, so meaning that it has a lower collision frequency. So using this calibrated season-based aggregated collision frequency models, we can then determine what will be the mean collision frequency given the material cost of routes. So we can come up with the two different scenarios. One scenario with the do nothing scenarios, which in that case, material cost of route will be 0, and then winter maintenance case scenario will be actual material cost of route that was used, and then you can quantify the effect of we can quantify the benefits of winter maintenance operations using season-based data sets. Although it's very simple to use, it has several drawbacks, as you can tell. First, the model can suffer from underestimation or overestimations, since the entire data has been aggregated on a seasonal basis, and because of these reasons, not only the data pertaining to winter storm events are accounted for, but also those that occurred during snowstorm periods. So then we are pretty much using all the data sets, not only representing the data set that happened during the snowstorms, but also that happened during under normal conditions. So this may not be a true representation. So this could lead to overestimation and underestimations. And also the weather condition in this model is represented by some average measure, which may not necessarily capture the underlying weather conditions at the time of the snowstorm. Since there are different winter road maintenance activities conducted as per varied road and weather conditions, using a single average cost, in this case maintenance cost, is not capable of examine the relative benefits of alternative winter road maintenance practices or policies. To address the shortcomings of the aggregate approach, another approach called event-based or disaggregate method is used to model the safety performance of a highway over an individual snowstorm. So by taking this event-based approach, the different winter road maintenance scenarios, including policy standards, level of service, methods, whether it's salting or sanding, the materials can be represented at sufficient level of granularity. Okay, so event-based modeling technique shows how many collisions may occur over an individual snowstorm over a section of a highway. So Osman and the research team at the U of Waterloo are among the first to propose the disaggregate approach. And what they did is that they developed an extensive set of storm-based collision frequency and severity model for using large set of data sets in highway, representing highway in Ontario, Canada. And what they used they used the hourly data from 31 patrol routes whose length in total is nearly 2,000 kilometers and over 6 winter seasons, and they're more than 10,000 side events, meaning that they're events in this case we consider event to be the event that is associated with the snowstorm conditions. And there has to be some kind of precipitations, obviously. And in their study, a new variable called RSI was introduced and then used. So for those who are not too familiar with what the RSI is, that the RSI is a surrogate measure of a road surface condition that varies between 0 and 1. And then you can just think of this as a sort of a friction measures. And this is used to represent the overall road surface condition of a patrol group. And what they use the typical generalized negative binomial model to model the collision frequency, as you can see here. So the negative binomial models entail some assumptions that it has to follow the binomial distributions, but it has been extensively studied in the previous research that negative binomial models it actually works pretty well in estimating the mean collision frequency. So some of the variable included here is visibility coming from road weather information system data, and RSI and exposure. This represents the traffic exposures and other atmospheric variable, including temperature, wind speed, total, or hourly event-based or hourly precipitations. So I highlighted this RSI because the RSI was found to have the largest effect on collision, and this makes intuitive sense since road surface conditions are one of the main factors that contribute to changing the driving behavior during inclement weather events. The RSI also has been considered as one of the most important performance measures that represents the effectiveness of winter road maintenance services. I think that Tina in the previous webinar have covered the importance of the RSI or some performance measure that represents the road surface conditions. as a performance indicator. So, our goal is to really establish a clear link between how the RSI how the collision frequency is affected by the change in RSI. And then here you can see that it has one of the most influencing factors with the -2.2. So this is the one of the most critical part is to make connection between the road surface condition and how it affects the winter accidents. So as I already showed you, this basically represents the RSI developed by Usman back in 2011. So it has their linear relationship. The surface index changes with respect to different categories of weather, and then he actually used a lot of data set to establish this empirical relationship. There's actually a linear relationship with different classes. So bare and dry would represent 1, and icy, whereas icy would represent 0.1 or even less. So this is the indicator that we can use to see how the surface condition, which is also affected by winter weather, as well as winter road maintenance operations or services, have on the impact it has on the road safety. Okay, maintenance operations also have a direct effect on the road surface conditions and thus the safety of a highway. So as a result, the timing of a maintenance operation is expected to have a significant impact on the safety effect of snowstorm. So here's a hypothetical example for illustration purpose that we can use we can quantify its benefit using the developed calibrated models that I showed you earlier. So at the start of the event, surface condition is bare, dry with the RSI of 1, and at the start of the first hour. At the end of first hour, the road surface condition, snow packed with ice. So here, like in this case, end of 1 hour. And then for the case where the maintenance, in this case, we assume that maintenance starts from the end of 1 hour, and then road surface conditions improves over an hour. But it actually, the quality, the surface condition also deteriorate as the time elapsed. So this is the hypothetical situation that we have created to just exemplify how the model how the calibrated model can use to determine the benefits. Since this is an event-based model, it is important to define what the event is, as I already mentioned. So in the study by Usman in 2011, their research team defined the snowstorms using bare pavement status and how it varies with respect to road weather and surface conditions. And maintenance activity is shown in this diagram. So trim and timing here. So you can see in this diagram, you can see the calculation of benefit with maintenance. So on the y-axis, we see the mean number of accidents, and then how it changes with respect to the time event elapsed. So the line represents the without maintenance, and then the red line represents the maintenance at hour 2. So this figure, this can be the so what we had in RSI can be nicely translated into the mean number of accidents. You can see that there's a very similar pattern, right? And this is obvious because if you look at the calibrated model that I introduced earlier, it has RSI was found to be one of the influencing factors that contribute to changing in the variation in number of accidents. So we can see that by doing it, just simply taking the difference between these two, we can then quantify the benefit of the maintenance operation, particular maintenance operation that have been that started at the end of hour 1. Okay, with the model, we can also conduct what-if analysis. For instance, we can estimate what would be the benefit of reducing BP recovery time. This is something that I already mentioned before. And bare pavement regain time is considered to be one of the most important performance measures. And then also it's got to do with the level of service so target level of service, what the maintenance agency want to achieve. So given with the models, we can actually conduct the what-if analysis. So in this case, we present a hypothetical situation where what if we reduce the BP recovery time from 8 hours to 7 hours? So in that case, we can reduce, although it will cost a little more for the maintenance agency to do this faster, or even start the operation a little early. then we can, with the reduction in 1 hour in the BP recovery time, we can actually estimate the expected reduction in number of accidents. So this 1 hour makes a huge difference. We have about 0.8 accidents that is expected to be reduced for Highway 401, and then Highway 401, and then QEW and QEW here. So again, this is just for illustration purpose. So takeaway lesson here is that with the model that we developed, we can actually quantitatively assess and quantify the benefits, and then we can even conduct a what-if analysis based on the given LOS or given the target LOS as well too. So safety, of course, is a one-sided story. I'm going to now move on to modeling winter weather, modeling the winter mobility effects. And as you know, the winter weather increases accident and also reduces highway capacity and speed, and therefore this will lead to increase the traffic delay. We all know that the winter road maintenance can help reduce this mobility effect, but the question is again how much we can reduce. So before going into the details of the modeling process, I should emphasize the fact that the traffic delay caused by winter weather can be captured at two different levels of aggregation perspectives, and they're microscopic and macroscopic. So I'll talk about this momentarily. And microscopic effects are reflected in the change of individual drivers' behavior, such as car following distance, speed, lane changing behavior, etc. Whereas the macro effects of winter weather are investigated as a whole and then described as the aggregated outcome of all travel. And some of the important macroscopic measures include the traffic volume, density, capacity, travel time, what else? The speed, free flow speed. And obviously we know that winter road maintenance help reduce the mobility effect here, right here. So we want to establish a link between this and how it affects the traffic delay in a using microscopic and macroscopic measures. Here's an example that uses the speed as a function of a snowstorm effect. The dotted line represents the median speed that you would expect under normal conditions. A red line represents the median speed under snowstorm events. And the space between tells us how much speed was lost over the entire snowstorm. But we can then calculate the total area representing the amount of speed lost and use it to determine if the maintenance standards have been met. And let's take a look at the effect on traffic volume as well too. Very similar. So we basically use the dual loop detectors, and we estimated we plotted the vehicles per hour. So the traffic volume over time, and then so dotted line represents the normal volume, and the solid line, the red line, represents the volume that observed under the inclement weather events. And similar to the one that we saw earlier, the space in between tells us how much volume was lost over the entire snowstorm. We can also calculate the total area that represents the amount of volume lost and use it to determine if, once again, the maintenance standards have been met. And we can also examine how traffic capacity will change as a result of snowstorm. This particular example shows the speed and capacity relationship before or during the snowstorms. Here, the y-axis represents the speed. We have a speed on the on our x-axis. We have a flow in vehicle hour for all lanes. So this also is obtained in the congested flow, so that we can obtain the capacity then. In the graph, we have blue and red line representing normal and event flow. This represents the event flow, snowstorm, and normal flow. And as you can see, we can have a capacity. We have a capacity of about 6,000 vehicles per hour per kilometer under normal conditions, whereas the number has reduced a lot, taking only about 4,500 vehicles per hour for all lanes. So this comparison demonstrates the amount of capacity lost. Again, this can be used as a key indicator for measuring the performance of winter maintenance and make more informed decisions on what kind of operational strategies can be made to better mitigate this effect on traffic capacity, winter weather on the traffic capacity. Okay, just like how we previously modeled the impact of winter weather on traffic safety using a set of independent variables that will affect the variation number in the number of accidents, we can also follow the same idea and quantify the magnitude of weather and maintenance effect on traffic mobility. And one of the main mobility benefits realized by winter road maintenance is the reduction in travel time of individual travelers in the network being affected by snowstorm. So this change in reduction can be estimated using a macroscopic traffic analysis that compares the speed difference from the two hypothetical winter road maintenance scenarios. As depicted in this figure, let's consider a particular highway section under a particular event. Using the equations shown here, we can calculate the total travel time saving for this particular event. So we have hypothetically created the two different scenarios, winter maintenance scenarios, and for which this will cause the average speed A, average speed B, and then by using this equation, we can calculate the travel time saving. So length, it's TTS, or the total travel time saving, can be expressed as a function of the QH, which represents the total traffic volume, and this is the offset variable, and L represents the highway sections, and S1 and S2 represent the average traffic speed of the road section in the H hour under winter maintenance scenario A or B, or in this case 1 or 2, I should say. So, okay. So in order for us to use this, in order for us to quantify or estimate the travel time savings as a result of winter maintenance, using different winter maintenance scenarios, we have to be able to estimate the average traffic speed for given scenarios. So for this, Donner back in 2012 have developed a traffic effect model, traffic speed effect models that is expressed as a function of these different independent variables, include the visibility, wind, hourly precipitation, and temperatures, and a volume capacity ratio. This is another surrogate measure that represents the level of service. So you can see that I also highlighted the RSI, which was found to be one of the highest contributing factor that affect the traffic speed under the inclement weather conditions. So 16.972. So you can compare the magnitude of its impact that it has on the traffic speed compared to other variables. So the second mobility benefit is the amount of traffic on highway affected by winter weather and winter maintenance operations. So we've talked about the total travel time saving, but not only that, we can also expect the traffic volume reductions. So this can be calculated by determining the reduction in traffic volume on a highway during specific snow events as compared to the traffic during the same day of the day, same time of the day, or same day of the week, or same week of the month under event-free conditions. So we have two different scenarios. So one is the event conditions, and then one is the event-free conditions. And this can be translated into mobility benefits. So here we have also, since the traffic volume needs to be estimated for Q2 scenarios, which is which represent the event scenario. So Donner, this author who calibrated the traffic volume effect model using the same Ontario data set used for calibrating collision frequency. So as you can see, the resulting model represents the so again, this is traffic volume models. The Q naught represents the offset term, the volume that we expect under normal conditions, and function of this visibility, wind, and precipitation. Again, the RSI is found to be one of the most contributing factor that affects the variation in traffic volumes under different weather conditions. So the same example used previously in the safety analysis, also used again to illustrate the difference in the mobility effect of two winter maintenance scenarios. So for illustration purpose, again, I've used the Donner's mobility models to quantify the mobility effect on the maintenance operation timing. So you can see that it's exactly the same example that I showed you earlier. So at the time of at 1, the snow starts at event 1, and then maintenance operation kicks in, and therefore the RSI which represent the overall condition of the road surface. And then it goes up, and then it also deteriorates as a function of time. And then for traffic volume reductions, scenario A with winter road means QA. So this is estimated traffic volume, which is estimated to be 30,525. The scenario B without winter road means. What if we don't have any winter road means? Considering the RSI using the same model that we calibrated, this estimated to be 28,695. So the additional number of vehicles so therefore the additional number of vehicles that are expected to travel due to winter means would be about 1,830 vehicles. So this represents the additional number of vehicles that can travel under these conditions. Otherwise, it would have been canceled because of winter road means operations. So sorry, let me clarify this. This represents the additional number of vehicles that could travel if it wasn't for the winter maintenance operation. So if there is no maintenance operation, this many vehicles would have been lost, or this many vehicles, the trips would have been canceled. So in this way, we show just a simple example to illustrate how the mobility effect of how the treatment timing changes with respect to mobility on the mobility effects. So for travel time saving, using Donahar's traffic speed equations and total travel time saving equations, we can calculate the total travel time saving TTS for each hour. And since the total duration of this particular event was assumed to be 8 hours, the maintenance starts at the service at the end of 2 hours, as already mentioned. And you can see that the TTS increases at hour 2 until it reaches hour 4. So here, the TTS total travel time saving with or without the WRM actually changes until it reaches its peak, and then it's actually deteriorates because the services are done. And this bottom figure graphically illustrates the total travel time saving that are expected from the maintenance operations for this particular storm event from 1 to 8 hours. The shaded area in this figure represents the total travel time saving, which are about 109 hours that can be saved by individual vehicles that travel on this network. Okay, what we have so far talked about is the modeling approach using macroscopic measures such as speed and traffic volume. However, the macroscopic impact on traffic flow as a result of the inclement weather events are triggered by individual driver behavior changes. This so-called microscopic driver behavior is also controlled by or dictated by different microscopic traffic parameters, including car following behavior and lane changing behavior, gap acceptance, acceleration, decelerations, etc. And because of their limited study conducted in the past dedicated to modeling the driver behavior, because of mainly due to the complexity of nature of human behavior and difficulty in gathering the microscopic data, we'll talk about how this can be done using simulation approach. So micro level investigation is necessary when we want to implement traffic control strategy, including signal timing adjustment during inclement weather events. So in order for us to make more informed decisions on the implementation of these different operational decisions, we need to gain a good understanding of the effects of the winter weather and winter remains, the microscopic parameters that explain how individual drivers will change their driving behaviors in terms of car following, headways, and lane changing behavior, etc. So what's included in the chapter is the basically the study that was done by I forgot the Shutter at the University of Waterloo that uses the implementations software called the simulation software called implementations to estimate the travel time saving. Now obviously there's some drawbacks that detailed analysis has to be carried out using more variables, but this still illustrates the possibility in estimating the total travel time saving using microscoping measures too. So when you compare the microscoping measures versus macroscoping measures, microscoping measures are more towards the helping decision makers make more informed decisions on the like a strategic operations, like the signal timing or signal timing optimization, so on and so forth. Whereas the macroscopic one, it is intended for the highway agency to better plan and manage the entire highway systems. Okay, this section shows an application of the developed mobility impact models for quantifying the mobility implications of different winter road maintenance policy and programs. And then a case study is developed to demonstrate the applications or applicability of the model developed using the 3 winter seasons of snow event data and 21 patrol routes. And then we assume the RSI of 0.6 as the target level of service. So meaning that for all, no matter what, our goal is to reach the minimum RSI of 0.6, which represents what can be translated into level of service. For this, for the travel timing saving, we assume $20 per hour as the value of time for calculating travel time saving data, and also we have used the $10 per additional trip made for this calculation. This is very hypothetical, and then because the data that we use to model this is only represent 13% of entire study area, but we still apply this to the entire network to see how this can be done. And so you can see that the large scale mobilizations, based on the assumption that we had, based on the assumption that we can keep whatever the RSI that we need to keep, we can expect to have this much of a benefit in trip making utility and also travel time savings. So this is as a result of a speed calculation. This is as a result of traffic volume calculations. So again, in this webinar, I try to answer these important questions. As for the first one, we've talked enough about not only can winter weather have a detrimental impact on safety and mobility, it can also deteriorate the quality of our environment as well as the performance of our transportation system. So a lot of decisions have to be made in the winter road maintenance operation at the strategic level as well as at the operational level, and it has we all know that it has significant financial implications. So in order for us to make more informed decisions on this, it's important that we have a quantitative understanding of what safety and mobility impacts are. And so by developing models that quantify the safety and mobility effects, we can help a winter maintenance agency develop a sustainable winter road maintenance program that entails the cost-effective policies and operational decisions. We also talked about the data needs. We also talked about the factors affecting traffic safety and mobility. And one of the critical factors that we found was the RSI, which represents which is a friction-like measures that represents the surface condition or surface states. And we also talked about a few different methods for quantifying such effects, and using aggregate data sets or disaggregate approach or aggregate approach, or as for the quantifying the impact of the traffic mobility. We also talked about the microscopic modeling approach, and then very briefly, and also macroscopic modeling approach. So with that said, I'd like to conclude my webinar. So if you do have any questions, please let me know.
Right, there's several questions, including two from start with two from Zhangmin Shi, and I'm going to unmute you, Zhangmin, so you can ask your questions yourself. Zhangmin?
Yes, can you hear me now?
Yeah, I can hear you.
All right, really nice work. Of course, I understand, there's a time limit, so we didn't get a lot into the details. So one question is related to that event-based model, I think, for quantifying the safety benefits.
Okay, yeah.
I was wondering, because you mentioned the RSI was the most important independent factor, and yeah, this one. So I was wondering whether or not before you developed the model, the independent variables were normalized, like say between 0 to 1 or something like that. So that
even other independent variables like visibility.
Yeah, all of them. Like otherwise, the ratio really doesn't mean anything unless they're normalized, right?
I totally understand. I mean, unfortunately it's not something that I could answer because I was not directly involved in the modeling procedures. But I don't think it has been normalized because we still keep the units like visibility and kilometer exposures, like which is expressed in terms of vehicle million kilometer traveled. I don't think it has been normalized. But I hear your points because if it's not normalized and then estimating using coefficient to judge whether it has the highest impact or not it can be questionable. But there's other slides that I didn't provide here, but then we actually found to have a very good relationship between the RSI and then the collision frequency. And then as I already showed you,
but from this slide you're showing, I'm guessing it was probably normalized because some of these like hours of data were like huge number. So the coefficient would be very small unless.
Sure, I mean RSI value only ranges from 0 to 1. It's a unitless data anyway, and exposure is a very, very large number. So given that it's a 0.377, I'm not quite sure, but I can look into that, but I doubt that it's been normalized. Yeah.
Okay, that's not a big problem. But another thing is like the goodness of the fit. Do you have something like R-square or something to show how good was the fit?
What I know is that basically by doing negative binomial models, developing in terms of collision frequencies, there's a goodness of fit measures, but I don't think it has been reported here. But what I know is that there have been all statistically found to be statistically significant using 94% confidence level. So I think these are the factors that have been found to be statistically significant. And then given the largest set of data sets, I don't think it will have a very high R-square value because it's such a large data set. And then even getting a 30 or 50% of 0.5 of R-score is considered okay in the transportation data sets. But again, I'm sorry, I don't have the
no, it's okay. I understand that you are not the main author of this piece.
Yeah.
Actually, a related question or maybe a comment is that if the R-square, because for safety models, I understand most of the time actually R-square is like 0.2 or 0.3, whatever. It's considered good enough. And with especially now the possibility of big data, machine learning, all that stuff. Do you think there's a possibility to use some other approach like artificial intelligence or?
Yeah, definitely. I think
to get a better correlation.
Exactly. I mean, that's something. I mean, using artificial intelligence or deep learning is definitely it's a current hot topic of everybody's looking into ways to model this. But yeah, I mean, I think Dr. Liping Fu, he's already started working, investigating how this can be done, estimated using deep learning approach, and then obviously you have to have a lots of data set for that in order for you to teach and train the models. But also there's also benefits of although you may have a better prediction power over this traditional modeling technique, but you also lose the how do I put this? Lose the sense of what kind of how each variables would affect the change in the mean collision frequency. For instance, if it's like a black box. You put visibility, RSI, exposure, everything inside, and then there's no way that you can quantify the effect of each individual variable and how much effect it has on the mean collision frequency, right? So, I mean, there's a pros and cons, but I definitely see a future there to include the to implement in the more sophisticated modeling approach like a neural network or a deep learning approach, which is all part of our artificial intelligence.
Yeah, because I understand, as we start to have more and more data available, probably, it becomes more realistic to use that kind of approach.
Exactly.
I totally agree with you. It's a gray box, if not a black box. So it's not as simplistic or elegant as this equation, which is very self-evident.
But as we
on this type of equation, I also have another kind of question. Like, it seems like the model sort of ignored the interactions or potential interactions between different independent variables.
That's a very good point. While answering your question, I thought of this acknowledging some of the limitations the modeling technique that we presented imposed. One is the lack of investigation on the interaction of these individuals variable have on each other. So there could be some confounding effects that attributed together to affect the mean collision frequency. But yeah, that's something that has to be investigated. And then that's a very good point, actually. So there could be a confounding effect, and then this has to be investigated. And I also have to emphasize the fact that, we always talk about this transferability, but this models that we developed, calibrated, were based upon using specific snow event data set that are collected over this highway network in Ontario. So I mean, it is questionable whether we can actually use this in estimating the benefit in let's say in Edmonton where I live. That's questionable, but the takeaway lesson here is that what kind of factor that we can use to assess the benefits associated with benefits of winter maintenance or winter maintenance on the safety. So that's what variable that we can use. And one of the critical variables that we found is the RSI.
Yeah, that's an interesting point. I think, if there were additional case studies done in other areas, of Canada and maybe even other countries, then maybe the model could be further enhanced.
Yeah, we can definitely work towards conducting more case studies to improve the generalization potential. I mean, that's inherent limitation with any research, I guess.
Okay. Yeah, actually, those are the only comments I had. Very nice work.
Yeah, I mean, it's not. I have to. It's not really strictly my work. It's my contribution is in more of a mobility part of it. But Dr. Fu has shared a lot of his insights and then also the slides, and then so for which I have to thank him. Yep.
All right, there's a question from Clay Adams, so I'm going to unmute Mr. Adams. Mr. Clay Adams, you can ask your question.
Hello?
Clay Adams? Oh, he doesn't have a microphone. He just stated that. All right, hang on a second. Let me read the question.
Oh, okay.
He posted earlier. The graphs that show the road condition deteriorating over time, did the crew just go out and plow and treat once and then go home, or how do you capture multiple treatments in the model?
Exactly. I mean, I guess he talks about this one. Yes. I mean, this is again a hypothetical situation that does not. That's a very good point. That does not really consider time that it takes for the maintenance operations to finish plowing. But here it's we have considered the road network that's very short in length. So we assume that maintenance operation just does it the finish. In this case, I think we assume the salting operations, and then there's a separate salting model for this and how it affects the RSI, which is dictated by, which can be represented by this how it deteriorates based on the salting model that they have. But that's a good point. I mean, but we didn't consider the total duration, total time that the maintenance operator needed to complete the salting operation, or whatever the operation that we need for this. But there's certainly, I mean, the framework that we have here can be extended upon, including different effects. I mean, how it affects the salting, how the salting operation affect the RSI is also has to be determined. And also how the sending operation would affect the RSI would also have to be determined too. But once we have that information, we have a lot of assumption going on here, but once we have that information, we can then quantify the safety effects of treatment timing, and also treatment, not only timing, but also treatment the types, right? Different treatment types, so plowing, salting, and sanding. And I say that it's not an easy task because the implication of a salting or the effect of salting has on the road surface condition also varies with respect to weather. If it goes below -11 or 12 degrees Celsius, then it's no longer effective. So then we have to apply the sanding operations. And this also changes with respect to the level of service that we have to maintain. So there's a lot of complexity that's involved. But for the simplicity of illustrating the example purpose, then this can be done given that we have all the models. We have the models that we have calibrated here, along with the maintenance, the performance of maintenance, and then how it changes over time. But that's a good point. Yeah.
His repeated comment is that this is not exactly how winter maintenance is done in the real world. But the understanding is, I think that you are talking in theoretical terms and you are aware.
I mean, I understand, but it's not how it's done. But then I don't think it's unreasonable that we assume that to perform a salting operation over a short stretch of road, we can. It's the time that it takes to plow or doing the salting operation can be negligible. So, but then I guess it has to be incorporated. But if it's not, I wouldn't say this is from a very theoretical perspective. This actually gives the platform onto which we can develop upon, and then include more variables, and then including the material types and application types, material types, and then the maintenance operation strategy, and so on. But then the framework is there to expand this and incorporate. But yeah.
All right. Are there any other questions? Be happy to, if anyone wants to raise their hand or post a question, I'd be happy to share it or unmute you so you can ask. All right. If no one else has anything, thank you very much, Dr. Kwon, for presenting today. Okay. I encourage everyone to attend our next session, which will be the search for greener materials for winter road maintenance operations, presented by Dr. Jiangmin Shi on August 12th.
Okay, thank you, everybody.
Thank you. I'm going to stop recording and end the session. Thank you very much.